going on, folks?
We just recorded 4142 and we're in the same clothes, not matching, and we're going to record 43, which we don't do often.
You don't usually get like us not wearing the same color. And I offered to change. She said, "Don't worry about it."
Yeah,
Probably wouldn't notice because like my shirt is my green is this is green, but it looks really dark. But
yeah.
whatever. And I
Today
got the
was villain day at our school, so I don't have costumes, so I just wore all black because that's what villains do. Archetypes.
gotcha.
Okay, so 4-3 is the introduction to probability, and today we're going to talk about how to calculate probabilities for events and their complements.
Well, don't you look nice today?
Oh, thanks. Are you ready to Mr. Bobby Eyes this one?
We're gonna have to do that again. Okay.
I thought it was so well done last time, so we're going to do it again.
Well, okay.
Probabilities of events in repeatable situations can be interpreted as the relative frequency with which the events occur in the long run.
Okay. So if I do something over and over again, I can use that to predict what's actually going to go on. Is that
So
kind
this
of
is just a repeat of 4142?
Yeah, pretty much. Like the more we do something, the more like it gets closer to the real thing. The problem is we can't really know that Miss Young is an 80% free throw shooter, like we talked about last. We can approximate that she's an 80% free throw. She might be an 80.1% free throw shooter.
Bala.
Okay.
All right. The sample space of a random process is the set of all possible non-overlapping outcomes.
I don't know how to Mr. Bobby Eyes this, but it's all the things that can happen, I guess. It's just random.
Everything could possibly happen on whatever it is we're talking about.
Yeah, all the possible ways things could fall. Okay, so if I'm doing a deck of cards, I'm going to pick a card out. There's 52 different cards. That's my sample space. All the ways things could happen, I guess.
If all outcomes in the sample space are equally likely, then the probability an event will occur is defined by this fraction. Number of outcomes in event E divided by total number of outcomes in the sample space.
All right, we really need to Mr. Bobby Eyes this. All right, because this is not going to that ain't going to work for me. When I want to figure out the probability of the way something can happen, I just need to figure out all the ways that what I want to happen can happen. And then I'm going to divide by all the ways that things could go down. Okay. So it's what I want divided by what could happen.
Right.
I'm sorry, my Apple Watch just buzzed. They're going to mute microphones during the next debate. Oh my gosh, that's going to be funny.
Oh.
What's the probability of muting Donald Trump?
Mr. Bobby, the probability of an event is a number between 0 and 1 inclusive.
Okay, so I think the probability of muting Donald Trump is somewhere between 0 and 1. And the Election Commission is going to try to do it. So I just thought that was funny. I'm sorry. I thought it was.
The probability of the complement of an event. What does the complement of an event mean?
Okay, a complement in math sense. You may have heard the complement in math in geometry as being, that's what, the 90-degree angle complement.
Yeah. My geometry teacher always used to say, if somebody's complimenting you, they're treating you right, like a right angle.
Oh my gosh, that's so bad. But a compliment is not like when I told Miss Young she looked pretty, that was a joke. Okay, that really wasn't a compliment in the statistics sense. It's the opposite of what. So you either, if I'm trying to figure out the probability of Miss Young making the free throw, the compliment would be the probability of her missing the free throw. So there's the opposite.
Right. And you can see it in a couple of different ways. So the complement of an event, you might see it like E with an apostrophe. You might see it as E with a superscript C. Or you might see it as not E. But basically the way you're going to find it is to just take 1 and subtract the probability of that event occurring.
Yeah, so we were talking about her and her free throws. If there's an 80% chance of her making the free throw, that's the event we're interested in. The complement would be the probability of her missing it, and that would be 1 minus 0.8 or 0.2.
Right, perfect. He's perfect.
All right.
So when we were younger, they used to do this promo all the time when you were buying sodas. You would like open the top.
Pop.
Soda.
Pop.
Soda.
I'm from Pittsburgh. It's a pop. Oh my God.
Anywho, you would look in the soda
Soda.
lid, in the pop lid, and there would be like a "You're a winner" or "Please try again." And "You're a winner" was just another soda on us.
Yep. And McDonald's will do this too, and they had all their games like little pill off thing. Everybody, they all have these games, and now you got to go online and redeem it for your stupid coupon, and nobody does that.
Let's
So,
say
but anyway,
has a statistics class, and there's 30 kids in the statistics class, and every single one of them is going to go buy one of these sodas and look at their cap. How many people, if the company says there's a 1 in 6 chance of winning, 1 in 6 out of a class of 30, how many do we think are going to have a "You're a winner" cap?
well, I would look at that 30 and figure out how many groups of 6 I have, and assume and hope that 1 out of each of those groups of 6 would win. So we would have 5. I would hope I would get about 5 winners if the claim was true.
Remember, guys, that probability is not a perfect science. So when they say 1 in 6 will win, they don't literally mean 1 in 6 will win for every group of people that are going to buy the soda. So we expect
many bottle caps, 1 in 6 will win.
Right. So
if you get to 6 people, you might not exactly have one person.
It's not like 6 people are going to walk up to the counter with a soda, 6 people in a row, and guaranteed one of those people is going to happen to pick one of those sodas. So is it guaranteed then that Mr. Bobby's class is going to have 5 winners?
I would hope that it would be close. I would want it to be, 4, 5, 6, 7. I wouldn't expect it to be 0 or 1 out of that many, but it could happen. So it's not guaranteed, but it could vary.
Right. It can vary, but we expect it to be pretty close to 5 winners in the class, right?
Right.
So the fact that only if we all open them and only 2 people have won, do we think the company is lying to us? If only 2 people in the 30 open their soda, look at the cap, do we say, Pepsi Cola, you are a liar?
That would mean only 1 in 15. If there were only 2 bottle cap winners, that would average out to be 1 in 15, which is a pretty big fib. But again, we're not talking about, is 30 many? What qualifies as many?
We will talk later in this course about like what's an acceptable number. But I
30 is a good start.
Mm-hmm. We definitely wouldn't want to have less than 30.
Yeah. 30 is not bad, but it's a decent start. But
so here's what we have to decide. We have to decide if 1 in 6 were absolutely true, what is the likelihood that only 2 people would win purely by chance? Like if 1 in 6 is true, that's super important. We're assuming that they are not lying to us. What is the probability or what is the chance of only getting 2 people? So how could we figure this out?
There's got to be some kind of formula or some kind of probability thing we can do. So let's try that.
How about we run a simulation?
Okay.
So now we need to come up with a simulation that has a 1 in 6 chance of winning. What do you think a good simulation would be, Mr. Bobby?
1 in 6 sounds like a number cube to me.
I also think it sounds like a number cube.
Now, back in the olden days of like the late 80s and early 90s, we actually would get out number cubes. And the day before the internets, we would actually get out some die and start rolling them bones.
And if we were in class, we would roll some number cubes because it's way more fun than just clicking a button on a computer. But sadly, we are not. So here's what we're going to say. We're going to say if you roll a 1, you were the winner of the extra Pepsi Cola. But if you roll any other number except 1, then you're a loser. I mean, you're not a winner.
You're a loser.
You're a loser. So if this is a simulation of 30, how many people win?
Well, let me see. I got 1, 2, 3, 4, 5, 6, 7. I think I count 7 ones. Am I seeing them all right? I think so.
Yeah. Okay. So that's only, now listen, guys. Remember the many, many thing? That's one trial. According to this trial, how do you feel about 2?
That's
Does
okay.
2 seem like enough? Does 2 seem like, does our class of 30 getting 2 winners match this?
No, this
No.
is more than 2.
This is a lot more than 2. This is
Yeah,
right?
it's like 5 more than 2.
Okay, so here's one sample. Let's do it again.
Oh, now I got to count again. Let's see, 1, 2 in the top row, 3, 4, 5, 6. Did I get 7 again?
7 again.
Woo-hoo! 7 again.
Okay.
Chris, slow down, girl.
2 is seeming not likely. What do we get this?
We got 5. We got 5.
We got 5.
I think.
That's what we expected.
Yeah, that's exactly right there. And I mean, if we get more, I'm not going to be upset. But if I get a whole lot less, I'm going to be upset. Am I seeing 3 here? I'm a little disappointed, but if your threshold was 2 for being upset, I guess I can't be upset. I'm close to being upset, but I can't be upset.
Right. So if I can get 3 purely by chance, can I get 2 purely by chance?
Possibly. I mean, anything's possible by chance. I mean, you know.
Right. So I could sit here and do a bunch of these, right? So
Right.
We're not going to sit here and do this again. Mr. Bobby, before we started recording this video, we actually sat here and clicked the button 30 times. Actually, I clicked it 15. He used his calculator 15 times. And together, we made 30 random samples for you. And we are going to show you a dot plot of the sampling, okay? So here's our dot plot that we got. So 1 dot on this dot plot. And it's important when you look at a dot plot that you remember what you're looking at. So what does this dot over 9 mean, Mr. Bobby?
That means that one trial, and I think that was one of yours, when you ran it, you got 9 ones out of 30 rolls. And that's exceptionally high, but you had one occurrence where you had 9 ones.
Yeah. And so each one of these dots represents another 30 dice being rolled, and how many winners you would get on that simulation of the soda problem, okay? So remember what we're trying to do. We're trying to decide if Pepsi Cola is a liar, okay? So we assumed that they weren't a liar. We rolled, and we rolled 30 times. We got 30 dots, and in those 30 trials, how many of them were 2 or less? Because more than 2 is fine, but like 2 or less is probably not great if we're assuming.
Yeah. But now if we look at it, I got 3 of them that were, and those were actually on my calculator. So maybe it's my fault. But there were 3 instances out of all, we did 30 occurrences, 30 classes, and only 3 of them were below the threshold. And we also noticed we had a 9, which was exceedingly high compared to the 5. So we had, it's going to happen spread out, but I want to point out that it's clustered. Notice that its center is around 5, and there is a lot of grouping near the 5.
So remember that our expected value was 5 because we said, okay, if there's a 1 in 6 chance of winning out of 30, 5 people are going to win, right? So we would expect the middle to hit at 5 because we assumed that was true. So here's what happened. 3 times out of 30 would have 2 or less people winning. 3 times out of 30. 10% of the time, purely by chance, 2 or less people won. So what do you think, Mr. Bobby? 10% of the time, is that convincing to you that they're lying?
That's not exceedingly high. That's a rare occurrence. Something that happens that small a chance could just happen by chance. And in this case, it actually did. Got a test. I did it on my calculator, and I guess got exceedingly bad luck. I guess my wife's bad luck rubbed off on me. She never wins anything. She always loses these contests.
So there's actually a percent where you can decide it's convincing. 10% isn't it? The general rule for deciding that something happens so rarely by chance that we're not convinced they were telling us the truth is what?
5%. If something happens that would occur less than 5% of the time, like if I make this claim, if Pepsi made this claim and then I do the experiment and I get a result that occurs less than 5% of the time, that's when I start getting suspicious.
Right.
At least then, that's a big deal for this course.
Right. This 5% threshold, and you're going to hear this over and over and over, is that statistically significant? If it is not less than 5% of the time, it is not statistically significant. Okay, because it can occur not pretty often, but it can occur purely by chance.
Mm-hmm.
Okay. All right.
We'll come back to that over and over. Trust us.
Over and over. So if you're like, what are they talking about? Don't worry.
Don't worry. We'll see it again.
That was your first little bite.
Yep.
Okay, so a couple of vocabulary words coming back to you here are sample space when rolling two six-sided number cubes. A sample space is all possible outcomes of the sum of two cubes, okay? So you can see here, back to this picture we were talking about before. We were talking about events before, and now we're talking about the sample space. And so the sum sample space is 2, 3, 4, 5, 6, and so on and so forth, okay? There are 36 ways, because they're individual die. There are 36 ways this could happen, okay?
A 2 and a 3 is not the same as a 3 and a 2.
Right. So the probability is, remember, it's that everything that we're talking about over everything possible. So if we're talking about the probability of rolling a 7, we need to, in our heads, think about, because this is obvious to you because I put the picture in front of you, but you need to, in your head, think about, like, how would I roll a 7? How many times and ways could I roll a 7? And then how many ways can I roll anything and add them together? So in this case, you can see here a 6 and 1, a 5 and 2, a 4 and 3, a 3 and 4, a 2 and 5, and a 1 and 6 means that there's 6 out of 36 possible combinations. So there's a 1 in 6 chance, 1 in 6 again, or a 16.7% chance of the sum being 7. Okay, so to determine the true probability of rolling an odd product on a set of die, we should list out all the possible products. Here you go. I've done it for you. Isn't that nice?
Oh, you're doing products. I've never, okay, never mind. You switched on me. I was like, what?
But I switched pictures.
You did? Okay.
Now we're looking at products that we could get. Complete the table. Did it for you. To show all possible products. In class, I would have actually made you sit there and fill this table out, okay? But for the sake of this video, we're not doing that. So use the table to find the probability of rolling an odd.
Well, I know there are 36 still possible outcomes, and I'm going to look for the odds. So I'm going to have 1, 3, 5 in the first column. So that's 3. And the second column ain't going to have none. In the third column, I'm going to have 3, 9, and 15. So there's a total of 6. I'm not going to have any in the fourth column. In the fifth column, I'm going to have 3 more. And then the sixth column, so is it 9 out of 36?
9 odds out of 36. So
now, do I have to reduce it? Can I just leave it as 9 over 36?
I love 9 out of 36.
I do too. Thank you.
But you know what? 9 out of 36 is potentially not what you would see on the answer to a multiple choice question. So while I don't mind 9 out of 36 as an answer, you do need to recognize 9 out of 36 as all of its many forms, reduced fractions and percentages and decimals too.
It's okay. I have a calculator.
All right. How about the probability of rolling a 4 or 5?
Probably on, so there would be the fourth row down and the fifth row down. So those, Wait, you want the product to be 4 or 5, or just rolling a 4 or 5 in one?
The product should be 4 or 5.
Oh, the product to be 4 or 5. Then there are, I think, 5 of those. Them guys.
So
There's
what if
fours.
I had said, okay, so there's 5 of them.
Yeah.
What if I had said 4 and 5?
If you want, well, I can't get 4 and 5 at the same time, can I?
Why
For a
not?
product,
Why
because
can't you get a product that adds to 4 and 5?
because every product is unique. Like there's only one answer to a product a multiplication problem, Miss Young. That's silly.
Yeah. In math, the word or and the word and, so important.
Mm-hmm.
The first time we're kind of talking about it here. And you can see this. Mr. Bobby, he counted. He said 1 and or he said 1 and he said 4 and 5. Okay, I can count that. 1, 2, 3, 4, and counted them. And what he was actually doing in his head is he was adding them together as he was seeing another one. In probability, the word or means you're going to add. Like you should see or and think, I'm going to add. I'm singing again.
Yeah.
So there's 3 out of 36 4s and 2 out of 36 5s. And when I add them together, I get 5 out of 36 and make that a decimal or a percent if you want. How about any number besides 6? Any number besides 6.
Well, there's a lot of them. So can I take the shortcut?
Please take the shortcut.
Okay, well, I can look and see that there are 4 6s. So it's easier in this case to actually figure out what's called its opposite, or wasn't there a word for that? There was like
Yes,
a really nice word for that, it was the complement. Turn it around. Okay. So it's instead of me counting up all those other numbers, I'm going to find those. There are 4 6s, 1 times 6, 2 times 3, 3 times 2, and 1 times 6 or whatever. And it's easier for me to count those and take that away from 1 than it is to count up all the others. So that's just being smart. And you don't need 2 math people to tell you that.
And it's probably pretty obvious, right? If there's 36 of them and 4 of them are 6, then 32 of them are not 6. So that's probably pretty natural for you.
Yeah.
But when you get probability tables, it might not be natural. So you'll have to really think about
No, there's sometimes that's not always obvious, but when it comes out, it's nice sometimes to use the complement.
How about any number from 1 to 36?
Well, that's a silly question. They're all between 1 and 36.
So the probability is
Uno.
Uno?
Yeah.
Yeah, absolutely. If everything is included, then everything out of everything is 1. Okay. Really quick, some basic probability rules. Remember that it is between 0 and 1. And if we take all the possible outcomes, then they have to all add to 1, which we're going to talk more about later. Okay. Yeah. But if we had every possible outcome and the probabilities of those occurring, and we added them together, we should always get 1. Probability of free throw versus not free throw. 80% plus 20% is 100%. It should be 100% every time if you've covered everything. Okay. The complement is 1 minus. The probability of an event not happening is 1 minus. We're going to talk a lot later about this concept of mutually exclusive. We're going to have this whole separate video for it. But it's a good time to kind of say, if we talk about 2 events being mutually exclusive, it means that they cannot occur together. For example, the probability of rolling a 4 and a 5.
Yeah.
And this is probability notation. So sometimes you're going to see this like P parentheses stuff. And this is just like the probability of A or B, which I'm hoping you saw in Algebra 2. But there's this union symbol when you might remember it from like interval notation, like negative infinity to 3, union, 3 to positive infinity.
Or Venn diagrams, maybe.
Or Venn diagrams, right. And it really just means like join these 2 things together or add them together, okay? So really quick, I think this is potentially the last question. Explain why this is a valid probability model. So remember what we talked about just a second ago. If it's a valid probability model, let me back up, then we would say, is every probability between 0 and 1? And do all the probabilities add to 1? So,
And so I would have to take all those numbers and add them all up and see that they added to 1. And Miss Young was nice enough to do that for you.
hey,
Yay.
find the probability that you don't get a blue M&M.
Well, the probability of me getting a blue M&M is 0.207. So can I just do the opposite thingy again that I did a minute ago?
Can you also add orange plus green plus yellow plus red plus brown?
I could, and we get the same answer, and it will end up. I mean, I don't think it's a big deal either way in this case, but 1 minus 0.207 is a little faster.
And here is your probability notation here. The probability of blue complement, because I'm saying I'm going to do 1 minus. If you do probability of blue without the complement symbol, then just add up all the numbers. What's the probability that you get an orange or a brown?
Now or means add. So I'm going to take the 0.205 and add it to the 0.198. Oh, I'm sorry, I read the wrong number. Brown is 0.124. Looking at the green. But anyway, you're going to mush those two together. What do you get when you have a brown and an orange M&M and you mush them together?
A pile of chocolate.
Yeah, you just get like, I don't know, because I'm going to swallow it down and it's going to be.
Yeah. So, and then can I get a brown and orange M&M?
And I can't, no, I mean, unless I take two of them and bite them in half and mush them, I literally push them together. But
they don't
come that way. They don't come that way. The M&M is either brown or orange. They're not like.
What is that called again? When they can't happen at the same time?
Mutually exclusive.
Mutually exclusive. Yeah. So, what's the probability that I don't get a red or a green?
Well, I'm going to take those red and greens and pull them out from 1. So I'm going to take 1 minus those two numbers, right?
Mm-hmm. Could I also add up blue and orange and yellow and brown?
Mm-hmm. Now I'm hungry.
I want M&Ms.
I want M&Ms. I gotta go to the gas station now and buy some M&Ms. Thanks, Miss Young.
Okay, so there is an assignment for you. It's not Khan Academy, so you're going to need to download this Google Doc. You can put it on your write it on paper. You can print this and write it on it, or you can type on it and submit it that way. Please use proper probability notation, which is the P of, like I was doing there at the end. Good luck. Have fun. I'm just realizing that I did not change my spinning from the last one, so I hope you like this twice. Bye.